Hi, my name is David, and in this video, myself and Michael will be discussing the article Cybersecurity, Nuclear Security, Alan Turing and Illogical Logic, written by Martin Hellman. In this article, Hellman raises multiple ideas and questions regarding his area of study and the importance it has in the world today. As the name of the article suggests, the main areas that are proposed within are cryptography and encryption, the history of how cryptography has evolved over the last few decades, the social and political impact of the work Martin Hellman has done in cryptography, and also how logic is used in an odd way for such important things as nuclear deterrence and cyber deterrence. In this video presentation, our group will talk about the main contributions raised in the article, giving some explanation behind the algorithms that are involved in each area, what research has or is being done in that area, and the impact this all has on our society. The first main topic that is discussed within the article is cryptography. So, what do we mean by the term? Cryptography is defined as the practice and study of techniques for secure communication in the presence of third parties called adversaries. More generally, cryptography is about constructing and analysing protocols that prevent third parties or the public from reading private messages. Modern cryptography is heavily based on mathematical theory and computer science practice. Cryptographic algorithms are designed around computational hardness, the hypothesis that a particular problem cannot be solved efficiently, where efficiently typically means in polynomial time, making such assumptions hard to break in practice by any adversary. Cryptography prior to the modern age was effectively synonymous with encryption, the conversion of information from a readable state to apparent nonsense. Prior to 1976, money transfers were just one of the growing number of applications which required encryption to remain secure. And as the internet grew to encompass millions around the world, a new problem emerged. At the time, encryption required two parties to first share a secret random number known as a key. So how could two people who've never met agree on a secret shared key without letting adversaries also obtain a copy? At the time, it was typical that in order for secure encryption communication to be effective between two parties, it was required that they first exchange keys by some secure physical channel, such as lists of numbers or letters written on paper. In 1976, Whitfield Diffie and Martin Hellman devised an algorithm to allow two parties to share a secret key over a network without using a physical channel. The algorithm is fundamentally a one-way function, a numerical procedure, which is easy in one direction but hard in the other. This algorithm then became part of what is known as Diffie-Hellman-Merkle key exchange. This key exchange enabled two parties who have no prior knowledge of each other to jointly establish a shared secret key over an insecure channel. This key can then be used to encrypt subsequent communications using a symmetric key cipher. So, how does Diffie-Hellman key exchange work? Well, Hellman and his partners knew that the algorithm used to create a shared secret key needed a numerical procedure. This brought them to modular arithmetic. For example, x mod p is congruent to y, or 46 mod 12 is congruent to 10. By using a prime modulus, such as 17, one can then find a primitive root of that number, such as 3 for our example, which has the important property that when raised to different exponents, the solution distributes uniformly around all integers between 0 and that prime modulus. So between 0 and 17 for our example. This number, 3, is known as the generator. And this is what makes the reverse procedure difficult, trying to find the discrete exponent of the generator needed to give a particular result. This is also known as the discrete logarithm problem. Using modular arithmetic in this way gave Hellman and Diffie their one-way function, easy to perform but hard to reverse. Given a result, one would have to turn to trial and error to find matching exponents. So, how hard is it to reverse this procedure? With small numbers, it's easy. but if we use a prime modulus which is hundreds of digits long, it becomes impractical to solve. Even if you had access to all computational power on Earth, it could take thousands of years to run through all possibilities. This is great since the strength of a one-way function is based on the time needed to reverse it. This leads us to the full procedure for key exchange then. So, given two nodes, A and B, who are attempting to communicate using Diffie-Hellman key exchange, A and B first agree publicly on a prime modulus and a generator, X and P. Then A selects a private random number Y and calculates A congruent to X to the Y mod P and sends this result publicly to B. Then B selects their private number Z and similarly calculates B congruent to X to the Z mod P and sends this result publicly to A. Now for the heart of the trick. A calculates S congruent to B to the Y mod P, which is the secret shared number, because B calculates S prime congruent to A to the Z mod P, which actually results in the same shared result. This result holds true since X to the Y to the Z mod P is congruent to X to the Z to the Y mod P. When you flip the exponent, the result doesn't change. Without one of the original private numbers, Y or Z, an external node will not be able to find the solution. With a large enough number, it is practically impossible to solve the logarithmic problem and to break the encryption in a reasonable amount of time. This solves the secure key exchange problem. It can be used in conjunction with a pseudo-random generator to encrypt messages between nodes that have never communicated. So, whilst Diffie-Hellman key exchange is still used today to secure a variety of internet services, it was suggested by research published in 2015 that these applications are no longer strong enough to prevent being compromised by some very well-funded attackers, such as the security services of large governments. After its creation in 1976, it was not long until the creation of RSA, an implementation of public key cryptography using asymmetric algorithms. RSA is one of the first public key crypto systems and is widely used for secure data transmission. RSA is an example of what is known as an asymmetric encryption. There are two types of key-based encryption: symmetric, or secret key, and asymmetric, public key, algorithms. Symmetric algorithms use the same key for encryption and decryption, or the decryption key is easily derived from the encryption key, while asymmetric algorithms use a different key for encryption and decryption, and the decryption key cannot be derived from the encryption key.
Shortly after the beginning of 1976, around a year before Rivers, Shamir and Edelman took Hellman and his students' work and made a public key crypto system known as the RSA, Hellman had begun to be of interest to the NSA, and they had begun to view the author's work as a political concern, as opposed to progress in the field of cryptography. In fact, the NSA felt so strongly about the matter that they phrased it as a grave harm to national security. Essentially, it would be deemed legally equivalent to exporting nuclear arms to a hostile foreign power. However, in opposition, Hellman felt so strongly in the other direction that he in fact deemed it also as a grave harm to national security if he and his students didn't publish their work indicating the move to a 256-bit key. The author and his two students became embroiled in a potential legal farce, with Stanford lawyers insisting that they could defend any case by citing the First Amendment's protection of free speech. However, the university could only cover the legal costs for the author, and as such the students were asked to not present their work. But by careful planning, they managed to appear on stage with the author as he declares their contributions, whilst also simultaneously taking sole ramifications. Nevertheless, the author went public with his and his students' work. Ultimately, if the NSA had indeed managed to silence his work, they might have fermented the internet as we know it today. Essentially, this wasn't the intention of the NSA head of operations, Admiral Bobby Ray Inman. He was simply dumbfounded by the motives of the author's research. His view was that cryptography, the study of sending secret messages, was only of particular use to spies and enemies. This view coming from 3 decades earlier when academics had helped win the war by breaking the Enigma code, enabling the Allies to read secret Nazi communications. The NSA therefore viewed it that Stanford researchers were freely disseminating information that might help adversaries in future to encode their messages in a way that the US couldn't crack. Rightly or wrongly, in the eyes of the NSA, this was a massive threat. Later in Hellman's article, he asks, how logical is cyber deterrence? Then immediately refers to nuclear deterrence as an analogy, a topic that Hellman has already researched and wrote about in his book, How Logical is Nuclear Deterrence? The 4 key points that are drawn between the two are that we must behave irrationally, that deterrence must be carefully defined, much more carefully than it seemingly already is. World leaders and others in power are impaired in their decision making, sometimes due to the lack of correct information. And how does one go about assessing risk of an event that hasn't happened yet but is bound to eventually occur? In other words, how do we protect against and prepare for future problems as the world evolves? Not only does Hellman talk about how we use logic in a seemingly illogical way, but he also references theorems that challenge the consistency and completeness of logic itself as a basis for decision making. He mentions Gödel's incompleteness theorems, which are mathematical theorems about logic that shook the world of mathematics when they were published and proved by Kurt Gödel in 1931. The theorems themselves fundamentally state that for an axiomatic formal system with sufficient complexity, this system will either have provable statements within it that contradict other proven statements, meaning that it is inconsistent, or the system is incomplete, and there are some statements that can neither be proved nor disproved. The implications of such theorems are huge, and so we can really trust the logical reasoning that our methods of cyber deterrence and nuclear deterrence are built upon. To conclude this presentation, and ultimately the summation of the paper, we can discuss the almost detrimental effect the illogical use of logic had on the author's life, with relation not only to his work situation, but more concerningly his personal life. In essence, the article can be used as a forewarning to many people who only see the world in a certain manner. There are different views, opinions, and ways to see the world and solve problems. We must ultimately take account for all views if we want to be around for years to come.